Hello, the members of this team are Emily Gandolfi, Catherine Kubiak, and Jacqueline Mattingly, and we built the Adjustable Limb Scanning Appliance, or TALSA. Let's start with a little background. Prostech is an orthotic and prosthetic company located in Troy, Michigan, and was established in 1988. They design custom orthotic and prosthetic devices which correct abnormal anatomy or replace missing anatomy. For the purpose of this project, we are going to be mainly focusing on the procedure used to create ankle-foot orthoses, or AFOs. An example of an AFO is shown in the center of the screen. Currently, AFOs are created based on a process that we call the casting process. A patient will come into Prostech and have their limb covered with a nylon sock. Next, the clinician will wrap the covered limb in fiberglass tape and wait for it to dry. The dry tape is then removed and taken to the technicians. The cast is then used to create a plaster model of the leg, which the custom orthotic is built around. It usually takes a few weeks for this process to be completed. Therefore, Prostech has started to use an alternative approach to increase efficiency of creating AFOs. Prostech is now using the scanning process, which uses 3D technology to virtually create a model of a limb. Thus, the entire process timeline is reduced from weeks to days. The problem is that there is not currently a way to effectively 3D scan full limbs. This is because the scanning process requires the patient to keep their limbs elevated and completely still while the scanning is taking place. This is extremely difficult for patients due to muscle atrophy and simply because it is difficult to stay completely still.
Prostech approached us with specific needs for the product. They wanted the product to be relatively portable, make the entire process more efficient, and allow the leg to be 3D scanned without causing any pain, discomfort, or deformation. Allowing the leg to be scanned without the deformation is important because it allows the scan to be more accurate. They needed a transparent, scratch-resistant material that can be scanned through, which does not interfere with the image acquisition. Based upon these needs, we developed certain criteria that the design had to meet, which will be discussed later in our presentation. Here are some of our initial drawings. We considered a shelf design, which consists of a sliding transparent frame. This was limited in the sense that the angle could not be adjusted. The tripod design incorporated angle and height changeabilities. We estimated that this design could lack stability. The table and slope designs both utilized telescoping legs, which were very similar. For the table design, the user adjusts the angle of the frame, whereas the slope design adjusts the leg height, which adjusts the angle. Finally, the music stand design includes a frame where the user can change out the material. The height and angle are adjustable as well. To decide which design we were going to pursue, we created a few matrices. One for the overall design, in which we rated based on the scannability, adjustment time, reduction in pronation and supination, foot stability, its weight, and how much it could support. The music stand design proved to be the best option. Next, the frame material was rated based on availability, scannability, cost, workability, visual, and durability. Lastly, the scan material was rated based on availability, with Prostech, safety, cost, and transparency. Initially, we made a 3D model with the Tinkercad software to get a visualization of our design. Then, in order to make our design more realistic to the dimensions, we created a model through the NX software. We then built a wooden model because it was our second best material, was cheaper, and we had the time to fabricate it.
Using our wooden prototype, we completed scannability testing to ensure that the design would allow for an easy scan. Both the design appearance and the vivac allowed for us to achieve the scan shown on the right. Therefore, we decided to move forward with this design. After completing the test, we constructed our final prototype out of aluminum. We made several alterations, adding locking hinges between the legs and arms, taking the cross-section out of the base, and painting TALSA black, which will further ensure that no part of the stand shows up in the scan. Unfortunately, due to the current situation, we have several steps that we were unable to complete this semester. However, we would like to finish them in the future. We planned on adding straps to the back of our design for added mechanical support. Following this, we would complete a final tip test. After the tip test, we would complete efficacy testing first at LTU and then at ProsTech. Finally, any additional changes could be made to TALSA. On behalf of Emily, Jackie, and myself, we would like to thank you for taking the time to understand TALSA. If you have any questions regarding our design or future plans, please email us.